Hello students, today we are going to start our lecture number 8 of module 2nd of nuclear physics. Okay. Up to the previous lecture, that is like up to the lecture number 7, we studied the shell model and the problems on the shell model. That is finding the spin and parity of the given nuclide. Now in today's lecture, we are going to study square wave potential. We are going to study square wave potential of infinite depth. Okay, what is our point today? Square wave potential of infinite depth. Now students, we already studied square wave potential in our quantum mechanics. Now at that time, it means when in the quantum mechanics we studied that the three particles are moving here. Okay, there is an infinite potential wave. Okay, and that particles is completely restricted to move here. Okay, means there is a constraint to the motion of that electron or that free particle. Okay, this is we already studied in quantum mechanics. Now see. Why here we are actually going to study the square wave potential of infinite depth. Now, as we saw in our previous lecture that the nucleus which is in that nucleus already fulfill the different shells that are already enclosed in some potential. Okay, means if this is a nucleus and this is different shells of nucleus. Okay, then this different nucleus fix some potential. Okay, that potential, what actually that potential happen, what actually the effect of that potential, that potential's effect is that nucleus are completely enclosed to that nucleus. Okay, means there is a constraint to that nucleus due to of that nucleus. Means we can say that nucleus is like a square wave potential, and in that square wave potential, number of nucleons are enclosed. Understand how? See here. See, means this is a nucleus. Okay, infinite potential, and in the different nucleons are enclosed. Okay, means to the motion of that nucleus there is a constraint. Okay, what is constraint here? Okay. See here, what is the constraint? Now, if this is the square wave potential of that nucleus and the number of nucleons are enclosed in this potential wave that is in the nucleus, then the constraint is that the potential U is equal to minus U naught when R is less than or equal to R. Okay, that is first one. Next is U is equal to infinite U of R. Okay. U of R, because this depends on R value. U of R is equal to infinite when R is greater than R. Understand? Means what is actually happening? See here. That nucleus which are enclosed in that potential wave that feel some constraint that they can't move that potential wave. Okay, because there is an infinite potential wave and they are enclosed in that potential wave. Understand? Now, I will study for the square wave potential we are finding the solution of Schrodinger equation. Now, here also same. Okay, only what is actually happening? This is a 3D problem. Okay. Now see, what is our Schrodinger equation? Our Schrodinger equation is this. Del square sin or minus h cross square divided by 2m del square sin plus e minus v of sin is equal to 0. Okay. Now students, see here. That is our Schrodinger equation for that nucleus. Okay. Now here we have to find the solution of that equation. Means this is differential equation, second order differential equation. We have to find the solution of this equation. Means we have to find the psi. Okay. This is 3D problem, that is psi should be depend on r, theta and phi. Now means we have to find the psi, r, theta and phi. Now as this is a 3D problem, what is our del square? Our del square is 1 upon r square dou by dou r square dou by dou r plus 1 upon r square sin theta dou by dou theta sin theta dou by dou theta plus 1 upon r square sin square theta dou square by dou phi square. Now we are going towards this finding the solution of psi, r, theta, phi. Now that is our del square. Now here consider L square as 1 upon L square as minus h cross square in bracket 1 upon sin theta dou by dou theta sin theta dou by dou theta, that is completed, plus 1 upon sin square theta dou square by dou phi square. Okay, consider this, that is our L square. Now if this is L square, then you can write del square as, see here this term is as it is. Okay, means 1 upon r square dou by dou r square dou by dou r. Now we are writing these terms in the form of L square, that is equal to minus L square divided by h cross square r square. Understand student? Means that is del square in 3D. 1 upon r square dou by dou r square dou by dou r minus h square divided by h cross square r square. Clear everyone? Okay. If this is our L square, okay. In that, if this is L square, then to write this term, we should have to divide this L square with minus h cross square and r square. Then and then only, if this L square, then h cross will cancel, and there will be the r square, and minus that will be plus. That's why that is our del square. Now second point, see here, write the del square in this form. Now we can simply write this equation in here as, see, del square. Just make the differentiation of this. Okay, means 1 upon r square as it is dou by dou r. If r square is constant and derivative of this, then r square dou square by dou r square plus 1 upon r square. Now this is constant and derivative of this, means 2r dou by dou r, and this term as it is minus x square divided by h cross square r square. Then what is our del square? Dou square by dou r square plus 2 by r dou by dou r minus h square divided by h cross square r square. Understand student? Now shall I remove this? See, okay. Now we have to put this value of del square here. Now what is actually happening? See here. Okay, we can write this equation as rearranged like this: del square psi plus 2m e minus b divided by h cross square psi is equal to 0. Clear everyone? Okay, means see here what is actually happening. Put the del square values here. What is value of del square? Dou d square by dr square of psi. Now first see here, if this is 3D equation of 3D coordinate Schrodinger equation, then the solution of this 3D Schrodinger equation will be in the form of psi r theta phi, and it can be written as r of r, okay, theta of theta, and phi of phi, okay, where this is psi r theta, where this term is called, this is a radial part of our solution, okay. When we are finding the solution of this 3D Schrodinger equation, we will got this psi r theta in the form of this. Then this r of r is the radial part of this function of that solution, and it depends on where this completely called as spherical harmonics. Spherical harmonics, and it depends on L and Mn, and it written as y L Mn. Understand, student? And this is written as r n L. Understand? Means now see here we have to put the value of del square, which is this d square by dr square, okay, r of r, as psi of contain this term, 3 terms, but derivative with respect to r, that is only radial part. Similarly, plus 2 by r dou by dou r, and again only r of r, because only r of r derivative will be happen, okay, minus L square divided by h cross square r square. What is L square? Actually, what is capital L? H cross under root L into L plus 1. Then L square will be h cross square. H cross get cancelled. That is, there is only minus L into L plus 1 divided by r square. Understand? Okay, student? And that is next. Means what is 2m by h cross square E minus, what is our potential P? U naught, that is plus U naught, okay, equal to 0. Understand, everyone? That is our radial Schrodinger equation, okay. Means what actually we done here, see here, first we are writing the constant of that nucleus which are moving in the nucleus square wave potential, and after that we are just writing the Schrodinger equation for that, and from that Schrodinger equation, which is second order differential equation, we should have to find the solution of that. That solution will be in this form, and in this form r of r is radial part, theta and phi is spherical harmonics, which is written as y mn, okay, and radial part is r mn, okay. Just important thing is that why actually we are calling this radial part or radial equation, because we are considering here only radial parts, okay, not theta and phi, okay. That's why it is a radial Schrodinger equation of that square root potential. Understand, student? Now see, actually means this is a radial equation, and the solution of that radial equation is, I can write here also. Shall I remove this? Okay. If this is a radial equation, this radial equation have the solution similar to as our Bessel equations, okay. What is our actual Bessel's equation? When we are solving this radial differential equation, then we have got the solution which is nothing but a under root k of r j l plus half k of r. Means when we are going to find the solution of this radial equation, then the solution of this radial equation is in the form of Bessel equation, Bessel equation, which Bessel equation? Spherical Bessel equation. That is spherical Bessel's equation of first kind. Okay, which is means exactly similar to our Bessel equation, which is written as J log kr equal to root pi 2 kr j l plus half of kr. Understand, students? See here, what is actually concept is that when we are finding the solution of this radial equation, we will got the solution this, and this solution is in the form of, or this solution is nearly analogous to the Bessel's first kind equation, which is this. Okay, we can see here both are same. Okay, means the solution of the radial equation is in the solution of the radial equation gives us the Bessel equation, the spherical Bessel equation, which is of first kind. Now see here, actually why we are going to study this, in this we just finding the energy of that nucleus which is revolving, or kinetic energy of that nucleus which is revolving in the nucleus potential, and which is written as a right there L square plus 2m E minus V. What is our V? Plus minus V naught, that is what? Okay, and from this, that is our K square. Okay, always. And kinetic energy is given by P square divided by 2m, where P is equal to h cross square K square. Just put the value of K square here. Okay, that will be our kinetic energy. Understand, student? Okay, or you can simply say that what is our kinetic energy of that nucleus which is revolving in the potential of that nucleus, or spherical potential of that nucleus is nothing but just kinetic energy is equal to h cross square K square divided by 2m, where K square is this term. Okay, and you can say that when r is greater than r, then that solution psi will be 0, and okay, when that r is nearly equal to r, then psi solution is not 0. Okay, because as there is a constant of infinite, that nucleus can't be come out of the infinite potential. That's why when r is greater than r, up to this, when r is greater than r means when r is greater than means in this region psi will be 0, and when r is less than or equal to r, then psi is not equal to 0. Understand, student? Means here why actually we are studying the spherical potential, to find the just kinetic energy of that nucleus which is revolving in the infinite potential depth of that nucleus. Okay, I hope you understand some points from this. Thank you.